And welcome back as we continue our cosmic journey. Let's go ahead and now use this to observe some distant galaxies. And when we're talking about distant galaxies, recall that we are actually going to be peering back in time. We can't directly detect the changes over time in individual galaxies because these changes happen so slowly. But we can observe many galaxies at different cosmic distances. And because we view at different distances, we can actually reconstruct the life story of galaxies since the universe began, even though we can't necessarily follow a single galaxy from infancy to old age, very much like how we can't do the same thing with stars. Now, this cosmic time machine lets us peer into the past to answer fundamental questions about where did galaxies come from and how they got to be where they are today. Astronomers refer to these galactic changes over time as cosmic time evolution. And there's three things that we kind of look at when we're trying to peer back in time, which is spectra, colors, and shapes. Astronomy is, of course, one of those sciences that measurements must be made at a distance. We can't instantly go out and go view another galaxy, just by getting in a spaceship. Fortunately, we do have a friend in electromagnetic radiation as a rich source of information, because the distance to a galaxy is derived from its redshift. And the conversion of that redshift to a distance really depends on the certain properties of the universe, including the value of the Hubble constant and how much mass it contains. Astronomers then can use that distance and the constant speed of light to infer how far back in time they're actually seeing the galaxy. Now, keep in mind that even though this is a really handy tool, many galaxies are so faint that collecting enough light to produce a detailed spectrum is currently impossible. So astronomers then use the colors of the stars to find the age. If we're looking at a galaxy and blue colors are dominating it, then we know the galaxy has hot, luminous blue stars, and the star formation must have taken place at least a few million years before. If the galaxy appears to be more of a red or a yellow, then we know that the young stars are now mostly old and yet red stars. They're yellow, red because they're moving down the HR diagram. These typically last a long time in the main sequence, and thus they had to have formed a billion years before the light we see now was emitted. Our third option is to look at the shape of the galaxy. Spiral galaxies, of course, can be distinguished from elliptical galaxies by their shape. And observation shows that spiral galaxies tend to contain young stars and large amounts of interstellar matter, while elliptical galaxies have mostly old stars and very little to no star formation. Elliptical galaxies turned most of their interstellar matter into stars billions of years ago, while star formation has continued into the present day in spiral galaxies. And that's going to give us a good thing to think about, which is the first generation of stars. Since stars are the source of nearly all the light emitted by galaxies, we can learn a lot about the evolution of galaxies by studying the stars within them. Star formation in elliptical galaxies began less than a billion years or so after the universe first started its expansion, and new stars continued to form for a few billion years. But then, star formation suddenly stopped in the ellipticals. When we compare distant elliptical galaxies with the ones we have nearby, we find that those ellipticals have not actually changed very much since the universe reached about half of its current age. And astronomers have discovered a few galaxies that are so far away that the light that we now see is less than a billion years or so after the beginning. Yet the spectra of some of these galaxies already contain lines of heavier elements, such as carbon, silicon, aluminum, and sulfur. These elements were not present when the universe began, but had to have been manufactured in the interior of stars. This means an entire generation of stars had already been born, lived out their lives, and then died. The new elements made in their interiors had to have happened through something such as a supernova explosion before the universe was even a billion years old, which means that we are missing a whole generation of stars. Now, of course, we do have a changing universe that we have to think about because the observation that all galaxies contain some old stars led astronomers to the hypothesis that galaxies were fully formed near the time when the universe began its expansion. If this hypothesis was correct, the most distant galaxies should have shapes and sizes very much like the galaxies we see nearby. Galaxies should then change very slowly as successive generations of stars with them formed, evolved, and died. Now, as the interstellar matter within them was slowly used up and fewer new stars formed, the galaxies would gradually become dominated by fainter, older stars and would look dimmer and dimmer. However, thanks to the new generation of large ground and space-based telescopes, we know that this picture of galaxies evolving peacefully and in isolation from one another is completely wrong. Much of the recent work on the evolution of galaxies has progressed by studying a few very specific small regions of the sky where telescopes have taken extremely long exposure images. And this allowed astronomers to detect very faint, very distant, and therefore very young galaxies. If, of course, we take a look at this image here, you can see we have a couple different galaxies that were observed by the Hubble Space Telescope, and they look very different from the present day galaxies. We don't see like spiral arms, disks, or bulges. Instead, what we see is galaxies that tend to be a lot clumpier than most galaxies we kind of see today. And while we might see some things that might resemble, for example here, that might have some start to some spiral shapes, if you look at these, they're kind of look more like what we'd expect to see like an interstellar cloud than what we'd see in a galaxy. Now, nearly all the galaxies we have shows that correspond to 11 billion light years or more, or less than 3 billion years old at that time. These are galaxies that are extremely blue, and that indicates to us that they contain a lot of young stars, and that star formation in them is occurring at a higher rate than in nearby galaxies. Now, observations also show that very distant galaxies are systematically smaller on average than nearby galaxies. When we look at galaxies that emitted light anywhere from 11 to 12 billion years ago, we now believe that we're actually seeing the seeds of elliptical galaxies before we got to their modern iteration, and we're also looking at more like the central bulges that now inhabit spirals. Now, over time, these small galaxies end up colliding and merging to build up today's much larger galaxies that we observe. So what such observations are showing is that galaxies have grown as the universe has aged. Not only were galaxies smaller several billion years ago, but there were more of them. Gaseous galaxies, particularly the ones that are less luminous, were much more numerous than what we can observe today.